Hey folks, 266 a little bit tricky. We have 7% interest and 12% interest, and we're trying to figure out the average interest. So, like most mixture problems, just kind of set up a little table. Okay, so we have 7% interest, 15,000. I guess we could have put the amount here. A couple ways you could do it. Let's put the amount here. So we have $15,000, and then also $11,000, and then the interest on the $15,000 was 12%. I'm just going to call it 0.12. And the interest on the 11,000, what the? Did I mess up already? 12% on the 11,000. 7% is on that. Double check. 0.07, 7%. 7% interest on 15,000, 12% on 11,000. And so he borrowed in total 26,000, and we're trying to figure out the average interest he's paying. Okay, so this is the middle column, so be careful. Remember, on the far left, this plus this is that, and on the far right, this plus this is that. But the middle column is just weird, so you just kind of ignore it. So on the far right, we have 0.07 times 15,000 and 0.12 times 11,000, and then x times 26,000. So we have, on the far right column, this plus this is that. So 0.07, 15,000 plus 0.12, 11,000. Why did I put a comma? Not one there? I don't know. Equals, this plus this is that. X times 26,000. So normally I'd say just keep going, but I'll just keep going. Let's see if I can get this one right. 0.07 times 15, 1, 2, 3 zeros, is 1050 plus 0.12 times 11, 3 zeros, is 1320 is equal to x times 26,000. Add these two together, plus 1050. So that's 2370 equals x times 26000. Divide both sides by that 2600. 26000 divided by 26123, and we get x is equal to 0.0911538. So they are wondering what it says, what's the average interest rate? Round your answer to the nearest tenth of a percent. So as a percent, so if this is x, so as a percent, that would be 9.11538 blah, blah, blah percent. They want us to round to the nearest tenth of a percent. So first I convert it to percents, and then they want us to round to the nearest tenth. So once you convert it to percent, the tenths place is right here. Okay, look next door to the right. Is it 5 or more? No. So 9.1%. Ta-da! Again, using the table. Okay, that was a tough one. Ooh, moving on to uniform motion. Okay, so if you're loving these problems, you are definitely going to love the uniform motion problems. Totally. 268. Lila's moving from Portland. Oh, so remember we have distance equals rate times time. Distance equals rate times time. So normally what we do is we set up our little table, and we have, we put the rate and the time here and then the distance here. That's usually what we do. And then sometimes either the distances are going to be equal to each other, or maybe the distances add up to something. So maybe there's a little box here sometimes. I'm not sure yet in this problem. I need to finish reading it. But just letting you know for how the problems work. So right now, either the distances are equal to each other or the distances add up to something. Okay, 268. Moving from Portland to Seattle. Takes her 3 hours to go by train. Mason leaves the train station in Portland and drives to the train station in Seattle with all Lila's boxes in his car. It takes him 2.4 hours to get to Seattle, driving at 15 miles per hour faster than the speed of the train. Find Mason's speed and the speed of the train. Oh, God. Okay, it takes 3 hours to go by train. Train, car. 3 hours to go by train. It takes 3 hours to go by train. Mason leaves the train station in Portland and drives to the train station in Seattle. So they're going the same distance. So these distances need to be the same. So I don't need this little thing yet. So it's just a little simple sort of box structure. So the distances are going to be the same. One person's taking the train, one person's taking a car. Okay, takes 3 hours by train. Mason leaves the train station in Portland. It takes 2.4 hours to go by car. And the car is going 15 miles per hour faster than the speed of the train. The car is going faster? I guess that makes sense. And the train stops a lot. Driving at 15 miles per hour faster than the speed of the train. Okay, so we need to put things here. So normally what we do, if the car's going faster, 15 miles per hour faster, we'd say the train, let's just give it a variable. The book likes to go with R. Okay, so if we're going 15 miles per hour faster, that would be R plus 15. So then how does the table work? This times this is that, this times this is that. And then they went the same distance, so then we had set these two equal to each other. Okay, so this times this is that, here we are, and then this times this is that. I'll put the 2.4 first. 2.4 R plus 15. So set them equal to each other, and you have 3R is equal to 2.4 R plus 15. I'll just keep going. 3R is equal to 2.4 R, distribute. 2.4 times 15, enter, 36. 3R, 2.4R, so let me subtract 2.4R, subtract 2.4R. So 3 minus 2.4 is 0.6. So 0.6R is equal to 36. Bring it over here. 0.6R is equal to 36. Divide both sides by 0.6. 0.6. 36 divided by 0.6 equals 60. R equals 60. Okay, so that means R, remember R is the train. So the train is going 60, and then the car is going 15 miles per hour faster. So 75 is the car, 75 miles per hour. So that's usually what they're looking for. How fast is the train going? How fast is the car going? They ask, find Mason's speed and the speed of the train. Okay, cool. There's the train. There's Mason. Mason was speeding. Okay. 268. Yeah, see, fun? Yep, you agree. That was fun. 270. Let's see. Local buses. Let's do 270. I think it's just like 268. I'll just set it up. Rate times time is distance. 2 buses go from Sacramento to San Diego. Okay, so it seems to me like the distances are going to be the same. Okay, the express bus makes the trip in 6.8 hours, and the local bus takes 10.2 hours. Time. Local. Okay, the speed of the express bus is 25 miles per hour faster. Okay, so what would you put here and here? The express bus is 25 miles per hour faster, so I would say this is R, and then the express bus is 25 miles per hour faster. Okay. Find the speed of both. Okay, so it's just like the last problem. This times this is that. 6.8. times r plus 25, and then this one 10.2 times r, and then the distances they drove are the same, so we set them equal to each other. 6.8 r plus 25 equals, and then we set over there 10.2 r dot dot dot. Once you get for r, that's the speed of the local bus, add 25, and that's the express bus. Ta-da! So keep going, you can handle it. 270. Oh my gods. Average speed. 274. Which one did I just do? 270. 274. Let's see what happens. Distance, rate times time. 274. Helen and Ann lived 322 miles apart. For Thanksgiving, they met at the other sister's house partway between their homes. Aha, aha. So this is one where we're going to look at the total distance. So it's like this. They're 332 miles apart. One sister goes this much, the other goes that much. So the total distance needs to be 332. So we're going to figure out this distance, and then on the far right, this plus this is that. Okay, 332. For Thanksgiving, they meet at the sister's house partway between. Helen drove 3.2 hours, so we have Helen and Helen drove for 3.2 hours. Ann drove for 2.8 hours. Helen's average speed was 4 miles per hour faster. Helen was 4 miles per hour faster. Helen was 4 miles per hour faster, so r plus 4. Ta-da! So now, it's very similar to what we were doing previously. This times this is that. This times this is that. But now we're looking at the total distance, so this plus this is that. Aha. So 3.2 r plus 4 plus 2.8 r equals the total distance, 332. Dot, dot, dot. Again, the difficult part is coming up with this line right here, setting up your little table, understanding that the distances had to add up to 332. And then right here, it should just be pretty straightforward. Solve for r, that's how fast Ann was going. Add 4, that's how fast Helen was going. Okay. Okay, I think that should be good for 2.4. Pause right here, and then we shall move on to 2.5. What do we have left in 2? 2.5, 2.6, 2.7? Oh, my lordy. Okay, pause right here.